you want to find the inductance of a coil of radius r, ultimately containing n loops, where you have an iron core. So the wire is wrapped around the iron cylinder for a total of n loops all the way around it. We start by just asking, okay, what's the inductance of a loop of radius r? Again, we're trying to find the inductance of this loop with the iron core, of this coil with the iron core. Okay, well, single loop, radius r, what's its inductance? The current in the loop is, assume the current in the loop is I, so that the magnetic field at the center is going to be mu naught I over 2r. That's at the center. Now, I say that, well, then the magnetic flux is going to equal the field times the area. Okay, well, this is the field, this is the area, and we know from the right-hand rule that the flux is perpendicular, or that the magnetic field is perpendicular to the loop. One thing I'm a little careless about here, I stated it, I said it, but I didn't write it down. Assume magnetic field is the same everywhere inside the loop. And that's not really so. That's kind of difficult to integrate the expression you get if you're anywhere but in the center of the loop, within the plane of the loop. You can easily get the magnetic field anywhere on the axis perpendicular, the central axis perpendicular to the plane of the loop. I don't think we've done that yet, but that's really rather easy to do, using the same ideas you do for the magnetic field at the center. And you don't even really have to do an integral, as it turns out. Well, that aside, we make this assumption. That's not accurate, but it's okay within a, certainly within a factor of 2. So it's not a terribly bad assumption. Okay? Now, that's equal to then to magnetic field times the area of the loop being pi r squared. The magnetic field's just mu naught I over 2r. Very easy to derive. We did it a couple of weeks ago. Okay, so we have then, this is the flux. We simplify that, the r divides the r. We end up with 2 pi squared, well, we can write it one of two ways. Mu naught pi I times r divided by 2. Or if we prefer, because k prime is easier to remember than mu naught, 2 pi k prime I r. And actually mu naught isn't all that hard to remember. It's just 4 pi times 4 pi k prime. Okay. Okay. Now down here, then, we have to use what everybody's responsible for knowing when they came to class the day before the last class, but seemed to be not a lot of knowledge of that. In any case, the EMF, due to a changing magnetic field or a changing magnetic flux, which is generally either caused by changing magnetic field or a changing angle of the loop with respect to the magnetic field, it's just the derivative of the magnetic flux. So the magnitude of the EMF is 2 pi squared k prime r, that's the magnetic field. Well, sorry, that's the flux. Okay, the flux is 2 pi k prime r times I. The only quantity here that will change with respect to time is the current I. So we take the derivative with respect to t, this is all constant, and we just end up with a di dt. That's very straightforward. And then we can also write that. I wrote it in terms of k prime, then I wrote it in terms of mu naught. You should be able to interchange these two notations, are two ways of expressing the magnetic permittivity. Okay. Well, in any case, that means that L is just this, because of course the voltage, the EMF, is just L times di dt, as we're familiar with. Okay. So I guess maybe I'll write that just to it's not the I dt, it's phi b dt. No. Maybe I ought to go back to bed. Had it right the first time. Definition of inductance is what you multiply by the rate of change of the current in order to get the resulting EMF. So again, the EMF due to the changing flux is L di dt, and we see that the EMF is equal to this times di dt, so this must be the EMF. Now I've expressed it in terms of mu naught, 1/2 mu naught pi r. That's for one loop, and that's in air or a vacuum. Air doesn't have much effect on the magnetic permittivity. Okay? There we have expression for L on the assumption that B is the same everywhere inside the loop. Now the exact expression is a little bit different than that, but I'm going to use this as a ballpark because what we're really after is we're trying to figure out what it's going to take for us to be able to observe the effects of the inductance of this particular configuration. Got a 70-pound chunk of iron cylinder with a bunch of about 200 feet of wire wrapped around it. Is that going to be sufficient? Is that going to have a sufficient inductance that we can observe its effects? And with the instrumentation we have, if we don't cheat and use an oscilloscope, which we don't have time to train on, it's fairly marginal whether we'll be able to do that. We'll see why. Now, the actual chunk of iron has N loops, and the permittivity mu is 1 plus kappa mu naught, where kappa is a number that just arises because the magnetic domains in the iron will tend to align with the magnetic field in such a way that they greatly enhance the magnetic field. Now, I have been able to measure the effect on this particular sample of iron. Haven't had time to measure it. But probably typical values of K for iron are between 10 and 100. Usually it's more than 10, usually it's less than 100. And I'm doing this out of memory. I think 80 is about the highest I've seen, and that might be for something else. But I know it's in the, it's a two-digit number. So that the inductance is what? Well, if you go to the iron, mu naught is replaced by mu, which is itself. I mean, adding 1 to something between 10 and 100 basically gives you something between about 10 and 100, about 100. So that this factor gets at least 10 times as big, but probably not 100 times as big. 40 or 50 wouldn't surprise me. N is the number of loops, because every loop contributes separately, individually, to the flux, which then contributes individually to the inductance. And we note that mu is basically, strictly speaking, if K is between 10 and 100, mu is between 11 and 101, but I say it's between 10 and 100. I'm sure it's still in that range, pretty sure it's still in that range. Okay, so for the loop as we observe it, here's the expression for the inductance, which I've rearranged to just mu times pi Rn over 2. And we want to estimate the inductance of the actual loop, which I allowed people to measure. So we'll go to that in a minute.